Hello friends, so welcome back. In this video I am going to explain to you about agitation. So friends, this agitation topic is one of the most important in chemical engineering from gate point of view, because frequently we see in various exams in various competition exam we find some questions related to agitation. As in previous year also one question was asked in gate 19. So friends, in this video, first I will give you an overview about what is agitation, and then I will explain you the design of an agitator, and then I will move forward with just one question of previous year of gate 19. So friends, first let us start. So this agitation is different from mixing. However, some students frequently gets confused between what is agitation and what is mixing. Basically, the in agitation includes agitation is a basically a mechanism in which we fluid force a fluid we force a fluid to make it move in a proper pattern. Frequently this pattern is proper pattern, and by proper pattern we generally mean a circulatory pattern. However, by mixing we imply just we take random any two fluids, or maybe just we mix it just randomly, means there is no any kind of proper thinking is there. So therefore this agitation is much more helpful in industrial point of view, friends. So this is what we mean by the word agitation. And friends, so and when we do this apply Buckingham pi theorem uh, for this agitation case, then what we find that there are various various things that affect our agitation. Suppose this is an agitator, and this is the height of the agitator, and this is the diameter of the agitator vessel tank. This is the height and this is the diameter. So, and when we apply Buckingham pi then we find that there are various parameters, like there is something called power, then there is the rpm, what is the revolution per minute or per second of this thing of the agitator, and then we find there is the diameter, and then there is the rho, means this is the density, and then there is something called g, that is acceleration due to gravity, and then there is mu, that is viscosity. So friends, now we find that there are 1 2 3 4 5 6 parameters are there, and when we found the basic dimensions, we find there are three. Basically three dimension means mass, as in density there is something of mass, and then is length parameter is in here and in diameter, and then is the time. So we find there is three parameters. Then when we uh, do Buckingham pi analysis, then we find 6 minus 3 implies 3. 3 means in this case, for agitator case rather, we will be having 3 dimensionless three dimensionless number. So friends, let me delete it for your better understanding. So friends, in previous slide we observed that there are three dimensionless numbers. Dimensionless numbers. Okay. Since there are three dimensionless number, now I will explain you what are these three dimensionless number. The first is the power number, that is NP. This is nothing but the power number. And the next is the Reynolds number. You might be already knowing about this Reynolds number. This is very much frequently encountered in fluid mechanics subject. And another is Faraday number. So this power number implies P by n cube d to the power 5 rho, while Reynolds number implies diameter square n rho by mu. How we get this? We know Reynolds number implies d v rho by mu. Here velocity implies n into d. Okay, and the next is the Faraday number, and Faraday number is n square d by g. Oh, so this our power number is basically the ratio of resistance force to inertial force, and by Reynolds number means inertial force by viscous force. However, this Faraday number implies inertial force by gravitational force, and when we put these forces and then we equate, we will get these Reynolds number, Faraday number, and the power number. So now let me first then come to the next important aspects. And next thing we can see, there is a curve of power number versus Reynolds number, and we find there should be a relationship between power number versus Reynolds number. And how this relationship is there? Basically, this graph is somewhat like this, somewhat frequently like this. Sorry, by mistake I have drawn it. This is somewhat, and for various other impeller size, this will be somewhat the above, below. So it can be anywhere with respect to various impeller diameters and etc etc. So basically our rough curve will be of this form. Okay friends, so we basically observe this we take roughly after up to roughly of Reynolds number less than 10. This is of Reynolds number less than 10, and for basically of Reynolds number greater than 10,000. So basically we observe through the experimental analysis that when Reynolds number is greater than 10,000, then power number remains constant. So this is the one of the most important insight we get from the experiments. And when Reynolds number is less than 10, this is in the laminar region. This is the laminar region when the Reynolds number is less than 10, and when the Reynolds number is greater than 10,000, this is the turbulent region. So in between there must be a region that is called transition region, when our flow will change from laminar to turbulent. This is the transition region. Okay, so then the next part will be the next part, we will get an insight of the two equation between of laminar and turbulent, and this is very much important from exam point of view, because frequently we get a question somewhere close to that. Then we observe in laminar region, when we multiply a power number with Reynolds number is a constant, and this happens when Reynolds number is less than 10, that is in laminar region. Okay, so when we multiply, we find that this np into Reynolds number is p by n square d to the power 3 mu is a constant. So some question might come where it will be given the Reynolds number is this, and you are required to find any kind of proper parameter. Okay, and then next we come to the turbulent region, and in turbulent case we observe, as in the previous graph, this graph, we observed that power number is constant. So basically your power number will be constant, k is equal to a constant. So this also give you another insight, and this you should keep in your mind from exam point of view. Okay, and then friends, let me come back to another important point. Another important point will be focused on scale up of agitator. Scale up of agitator. So friends, how we scale up an agitator? Scale up means, suppose this is the lab scale agitator, and we need to scale up from this lab scale to an industrial scale of similar nature. So what is the method of this scale up of an agitator? Okay friends, then here we take some kind of assumptions for the scale up purposes, and we take the first assumption is like, for this is an agitator, then this is the height and this is the diameter, and here we take an assumption that diameter is equal to height. So we will design our this scale up criteria for this special case, and this you should keep in the mind. This is the background. You should keep, some question might come related to this thing. Okay, and since we are designing a similar kind of agitator, we will just increase from this small scale to a large scale by a factor r. So suppose this is the small scale and this is the large scale, and this has the diameter d1 and this is the diameter d2. So we will d1 d2 will be r times d2. So basically our main aim will be to find this scale up factor, this r, scale up factor, scale up factor. This can be called a scale up factor. Okay. Now our main aim will be that how to find this r. So first we find this. Suppose this is a small scale agitator and this is the large scale one. This is a tank 1, agitator 1, and this represents agitator 2. Okay, so volume of the first agitator is pi dt1 square by 4. multiplied by h1. So this is h1 represents this height and this represents dt1. However, we will, since we are, I have shown you previously, we are taking a special case. So this will be by pi dt cube by 4 dt1 for diameter of tank 1. This will be the and for volume 2 we will be having this pi dt2 cube by 4. And since I told you here we have to find the scale-up factor, then how we will find this scale-up factor is nothing r by r equal to volume after scale up, and this is like below is volume before scale up to the power 1 by 3, or r is nothing but diameter of tank 2, that is bigger vessel of the divided by the smaller vessel. So this I told you previously, dt, this is the bigger one, is equal r dt1. So this is all about the scale up factor. Now I will explain you the special cases that come in this scaling part. So while designing an agitator, we need to design for a case. So we will design for our requiring to our case, or rather needs. So what are these needs? So let me explain you one by one. And the third thing is that you can this is the rather trick, like to do questions easily. This r to the power n is equal to n1 by n2. I forgot to tell you, this n1 is the rpm of agitator 1 and n2 is the rpm of the agitator 2. So this equation you can remember, this is the scale up factor, this is the rotation per second of agitator 1, and this is the rotation per second of agitator 2, and this and n is an exponent. So if you remember this simple basic equation, you can solve the problem very easily. However, if in case you forgot it, there is an other way round. So first, since I told you that I will be explaining you for various case to case basis, and then let me explain you the first. This n exponent is equal to 1 when for equal liquid motion or equal tip speed. So equal tip speed will mean pi d1 n1 is equal to pi d2 n2. This is very simple. For equal liquid motion, you can understand that equal tip speed means this thing, and when you do these things and you solve, then you will automatically get n is equal to 1, and you can require this for case 1. Now the second case is n equal to 2 by 3, and this n goes, exponent goes 2 by 3 for equal mass transfer. When we require mass transfer rates to be equal, which implies P by V, power per unit volume, is equal to constant. So when you put power divided by volume equal to constant for both the cases, this implies power of V1 will be equal to P2 by V2. This is power of agitator 2 divided by volume of agitator 2, P1, power of agitator 1 divided by will be constant. Then you will get same equation, this r to the power 2 by 3 and 1 by n2. So, and then one of the third equation is n equal to 3 by 4. This is for equal suspension of solids. Okay, and similarly is the case, and the another is n is equal to half for same surface behavior. Same surface behavior. Same surface implies Froude number equal to same for both. So this is one of the another criteria. So friends, I have already explained to you about the various 4 cases that will help you in solving this question. You can get these equation by substituting these things in our basic design equation of the not design equation, the power number and Reynolds number and Froude number, etc. So you can get it. So now I will just take previous year question of gate of previous year, this gate 19 question. So let me, this book is loading, and this is our gate 19 chemical engineering paper, and you can see this question is, yes, right here, 29 question. So the question reads as, a disk turbine is used to stir a liquid in a baffle tank to design the agitator. Experiments are performed in a lab scale model with a turbine diameter of 0.05 meter and a turbine impeller speed of 600 rpm. The liquid viscosity is 0.001 pascal second, while the liquid density is 1000, and the actual application has a turbine diameter of 0.5 meter and impeller speed of this much, and viscosity is given and liquid density. Basically, this is the of Scaleup problem. Our 2 things are given basically of smaller lab scale parameters, and we need to find of the difference between P2 by P1. And we know from design aspects that from and for similarity in operation, the dimensionless number should be same for both the cases. So this is, if you know this thing, that dimensionless number is same for both small scale and as well as in the large scale. So this is another important insight, that so we will take this power number will be same. So power number for small tank 1 will be equal to the tank 2. And when you put just these 2 things, and when you put this NP1 implies P1 N1 cube D15 rho is equal to P2 rho 1 N2 cube D25 rho 2. So these densities are given same in both the cases. And when we put P1 by 600, this even RPM is same when we go to the question. So P1 is equal to P2 by 0.05 to the power 5, 0.5 to the power 5. So P2 by P1, when you solve, you get 10 to the power 5. And this is option C is the correct answer. Let me show you this question again. Sorry. So this C is the correct answer. So friends, this is all about agitation and agitator Scaleup. If you understand this much, please hit a like button, and please like my page and share my page and comment. If you have any doubt, please comment. I'll be very much ready to help you. Thank you.